Good day. This presentation explains the design of a wastewater treatment for a pineapple processing plant. The following table shows the composition of pineapple wastewater from two works, Abdullah and Matt 2008 and Sasaki 1991. Pineapple wastewater contains mainly glucose, sucrose, and fructose. The waste contains very little nitrogen and soluble protein and elements such as iron, calcium, manganese, zinc, copper, cadmium, sodium, and potassium. Potassium is the most abundant element in the pineapple waste. Pineapple wastewater is acidic with a pH of 4 to 4.3. Most of the acidity is due to citric acid, with a significant contribution made by malic acid. Here's the table showing the composition of pineapple industry wastewater. The table is divided into the different composition of different groups. First, we have sugars. Second are the proteins, which are measured in terms of soluble protein and gel-del nitrogen. Third are the organic acids, which are mainly composed of citric acid and malic acid. Fourth are the cations, in which there are high levels of sodium, magnesium, manganese, and calcium. Fifth are the anions, in which chloride ion and phosphate are the highest amounts depending on the research study. Lastly, there's the pH, which shows that the wastewater is acidic. The following table shows the characteristics of pineapple industry wastewater as well as the standards set by the Malaysian government. The wastewater of the pineapple industry has a high COD, total suspended solids, and turbidity. It also has a low pH. Sources of liquid and solid waste during the pineapple canning process is shown in the figure. The liquid waste comes from the washing of pineapples, slicing of pineapples, and addition of syrup. Additionally, wastewater is also generated from spillage, washing of cans, tanks, cooling equipment, and floors. Now let's proceed to the block flow diagram of the treatment process. We begin by assuming that the wastewater to be analyzed is liquid waste, free from solids and other large materials. However, for safety measures, we allow the wastewater to undergo screening. According to the data, liquid waste consists of sugars, proteins, organic acids, cations, and anions. It also has a pH level of 4. With that, for the primary treatment, the liquid waste will first enter the aerated grate chamber, then to the primary clarifier. The grate chamber will provide oxygen to the water, which causes for the molecules to react and create an insoluble precipitate. Therefore, it treats cations and other organic matters that are present in the liquid water. Moving on, the said precipitate will sit for several hours before proceeding to the second treatment. The secondary treatment starts by putting the water in an activated sludge process to speed up the work of the bacteria in order to break down the organic matters such as sugar, proteins, and organic acids into harmless byproducts. After that, the water will proceed to anaerobic digestion, then biological denitrification to remove the chemical oxygen demand of liquid wastewater and anions respectively. Lastly, the tertiary treatment. To remove ammonia in water, it undergoes in a physical-chemical separation to separate its physical and chemical properties. Then, the water will be treated in a process called BNR or biological nutrient removal that occurs in the bioreactors. Thus, as the water passes through the three tanks, the phosphorus is removed and ammonia is broken down into nitrate and nitrogen gas. By now, all the components of the liquid wastewater has been treated except for its pH level. So with that, the soda ash or the sodium hydroxide injection process is applied to increase the pH level of water near neutral. For the disinfection, the liquid water is disinfected by ozone, which has greater disinfection effectiveness against bacteria and viruses compared to chlorination and ultraviolet. Now let's proceed to the process flow diagram of the wastewater treatment design. As mentioned earlier, the primary treatment begins by letting the wastewater flow through a screen. The screen removes any suspended solids carried by the water. The wastewater will then flow to the aerated grate chamber, which provides oxygen to form insoluble precipitates with the ions present in the water. Then it flows through the primary clarifier, which collects the insoluble precipitates and other remaining solids. As wastewater enters the anaerobic digester, the secondary treatment now begins. The chemical oxygen demand is removed in this equipment. As wastewater enters the aerobic bioreactor, oxygen and bacteria are provided to remove the organic matters. Then it flows through the secondary clarifier to remove the sludge. Wastewater will then enter the denitrification chamber to remove the remaining unwanted anions by creating insoluble solids. Then it goes through the secondary clarifier number 2 to remove the insoluble solids. As wastewater enters the biological activated carbon filter, the tertiary treatment now occurs. In this equipment, the gel-del nitrogen is removed. The wastewater then now goes through the biological waste treatment to remove the phosphorus content. Then, in a mixer, the sodium hydroxide is injected to increase the pH level of the water. Finally, wastewater undergoes ozone disinfection where ozone is used to kill the remaining bacteria. Then it is finally released as clean water. We based the process of our block flow diagram on the components of the liquid wastewater that needs to be treated. Then, we differentiated the contaminants effects on the discharge. After analyzing the effect, we researched different ways or processes that can prevent these effects from happening.